For the next example problem, we will still be working on the same corridor, Dunford Road. We analyzed it before as a single intersection and an urban street segment. And finally, we're going to perform a two-way stop control analysis for this intersection in the middle, which we previously modeled as an access point as part of the urban street. And all the data required for this problem is shown over here. So we have our turning movement volumes, truck percentages, picker factor, grades. And with that, let's get started with our two-way stop control module in HCS. We can start a new file. And on the first step, let's make sure we set our major tree direction as east-west. And we need to do this correctly at the beginning, otherwise we have to reset our lane modeling. In this case, we need to model what kind of median openings we have. And in this case, we may select whether left or through or left only. Since it's at the intersection, there is no through movement, so it doesn't really matter, but we can select left only. And that will enable us to model two-stage crossing. So back to the map, what we do here, minor street movements approaching the northbound approach, they may use this median opening here to perform this northbound left turn movement. And based on the geometry that I see over here, so if we look at the available width, which would be around 22, 23 feet, we can then determine how many vehicles can be stored here in the median opening. Based on my own judgment, I think only one vehicle can be stored, so that's going to be my input over here. And we also have a picker factor of 0.95. And these are all the inputs that are required in this page. Let's proceed to the next page, and we'll start modeling our lane geometries. So as we see in our problem statement, for the eastbound approach, I have one exclusive right, I have 3 through lanes, and 1 U-turn lane. For the westbound approach, I have 1 exclusive left and 3 through lanes. And for my northbound approach, I have 1 exclusive left, 1 exclusive right. I have 0 grade, so I can just keep it as 0. No additional features to model here, such as channelization or flared approaches. And we can then proceed to our traffic input. So for eastbound, I have 2 vehicles per hour for my U-turn demand, 2,400 vehicles per hour through, 9 vehicles per hour right. Westbound, I have 15 for left, 1,850 for through. Then for northbound, I have 13 vehicles per hour left and 127 vehicles per hour right. I have 10% trucks on every single approach. And nothing else needs to be entered here in this screen. For headways, headways are computed automatically. So based on the movements that I have provided in the lanes page, a certain base critical headway and base follow-up headways are assigned. So these are based on HCM suggestions. You may want to change them if you have your own local data. And then based on other adjustments such as grade and heavy vehicles, the software automatically computes the adjusted critical headway and follow-up headways. And these are the ones that will be used in the capacity equations for each one of those movements. For the adjustment page, we could enter pedestrian volumes, and we don't have any pedestrians in this intersection. And at the bottom, we can also check this box to tell the software the presence of any upstream signals that may cause vehicle platooning. As you have seen in the previous urban street example, we do have upstream signals, but for the first part of this exercise, we're going to skip that input. We're gonna model everything else as we discussed. And at the end, part 2, we're going to revisit this and we check this box so we can compare how those different inputs may change the results. And with that, we're done with our data input process. We can click report. And here we will see our typical report. So we have a sketch of my intersection. We have the summarized inputs, volumes, geometry. Listed in the table, we have our critical and follow-up headways and their internal calculations. And at the bottom, you'll see my performance measures. You'll notice, for example, not all major treat-through movements are listed here. For example, eastbound through, right or westbound through. Because they are rank 1 movements, they are assumed to have 0 delay. So they are omitted in the report, but they are used internally to compute delays for the approaches. Overall, I have 3 movements that are failing. I got a level of service F here, especially northbound. You have some pretty high delays, over 350 for left, over 150 for northbound right. We have our average delays and level of service for each approach. You may notice we don't have an average delay for the entire intersection. We can only access that by going to the text report. And then we go all the way to the very left line. And we have an average intersection delay of about 5, almost 6 seconds per vehicle, which is pretty low, but there are no level of service assigned to the entire intersection. As discussed in the coursework, the HCM advises against reporting intersection delay for two-way stop control because most of the vehicles, typically the major treat-throughs, they will have 0 delay, and when you compute the total average, you may expect a very low delay, but that can omit some of the operational problems that are happening, especially in the minor treat approaches, as you can see over here. And with that, we're done with the first part of our two-way stop control analysis. And remember, that's not considering the effects of upstream signals that we'll be discussing in the next part of our problem. For the second part of this example problem, we're going to revisit the same file, but now we want to consider what would be the effect of the signalized intersections upstream and downstream, and the effect the platooning created by these intersections will have on my two-way stop control analysis. So what we want to do, we want to revisit our model, but for the second part, we'll be entering those proportion of time blocked, as you can see here on the slides. And how do we get those numbers if we're doing our own analysis? Let's revisit our urban street segment file as we discussed in the previous module. And one of the options you can do here in streets, you can open the report menu and go to the access point report. So if you recall, this access point was the same intersection, but for the streets module, the intent was to calculate the delay added to the through movement. So it doesn't replace the two-way stop control intersection that we're doing right now, but those methods are interconnected. So if you go to the report, you can see the proportion of time blocked that is listed here, which means this is the proportion of time where the volumes that will be traveling through that intersection will be so high that they won't allow any vehicle to enter during that period. So I got those numbers, and that's what we saw on the slides. And let's now go back to the software, and let's return to the adjustment page where we want to check the upstream signal. And now we're going to enter those numbers over here. So we have for my westbound left 0.36. For northbound left, I have 0.49 or 40% of the time that's blocked. And for the northbound right, I have 0.36. And once we are done with that, let's return to our report. And let's see how my performance measures have changed. But overall, they were looking significantly better. Instead of 3 movements to level service F, we have just 1. But even with that movement, delays have still been reduced significantly. So in the next part of our problem, we're going to expand the discussion and compare those 2 results. Now, let's compare the results with those 2 approaches. On the left side, without considering the platoon blockage, the first part of the exercise, and on the right side, the second part of our exercise, considering the effects of platoon blockage. You'll notice there's a significant improvement. So for the westbound left, for example, my control delay was reduced from 87 to 33. So my level of service improved from F to D. Northbound left, my delay has been reduced from almost 360 to 75.4. So a very significant improvement, although it's still level of service F. And for the northbound right, I experienced a reduction in delay from 154 to 13, so very significant improvement, a level served from F to B. So how can we explain that even though you have a significant portion of time blocked, you can still experience some significant improvement in delays? We may want to go back to the urban switch segment file, and we can take a closer look at what's happening in our access point. We discussed that we got those proportion of time blocked. We can get a better sense what's going on in our access point by clicking this flow profile diagram. And by default, it shows arrival rates on the intersections, which use internally to compute arrivals on green. But for this example problem, we want to focus on what's going on in the access point. And you can see the forward direction, which is westbound, or reverse direction, eastbound. And this graph can give us a better idea what's going on over here. So for example, for the forward direction, the vertical axis represents the traffic flow, and the horizontal axis represents the time inside the cycle. So that's why you see the 140 seconds. So you'll notice for the second half of the cycle, you'll see some significant traffic volumes, which will correspond to signals discharging. Most likely, the through movements, the higher demands are within this period over here. And this portion of the cycle with higher traffic will correspond to my blockage. But on the other hand, when you have some peak blockage, that means for the remainder of the cycle, so if you look at the first half here, you'll see some periods with low volumes, and those low volume periods, they create several gaps, several opportunities for vehicles that are able to enter the intersection and clear the queues. So that is the part of the blockage that can actually increase capacity. So it doesn't mean every single input will increase capacity. So it really depends on the proportion of time blocked. But because it's a computationally complex procedure, we always recommend plugging in the numbers into HCS and let the software tell us whether operations improve or get worse due to the blockage. And with that, that concludes our analysis for this two-way stop control analysis. And this highlights how these ATM segments and two-way stop control, they are interconnected. So using all the tools and connecting them can always give you the most accurate and the best results for your analysis.